All right, I'm going to start by considering this building block integral, if you will. So it's going to be an integral along some vertical line in the complex plane of x to the s ds over s. And here I'm imagining that sigma is going to be a positive real number, and x is also going to be a positive real number. And t is thought of as being large. And we're interested in this integral, and in particular in error terms, depending on t and x for this integral, because this is going to let us deal with Dirichlet series using what's called Perron's formula. So let's get started on evaluating this integral using Cauchy's residue theorem. So this integral, the integrand x to the s over s, has one pole at s equals 0 with residue 1. So we're going to consider 3 separate cases for evaluating this integral. Case 1 is going to be when x is less than 1. So it's a real number strictly between 0 and 1. Then what we do, okay, we've got the one pole at s equals 0, and we've got our line of integration, sigma minus it to sigma plus it. So I'm going to call this segment C1, and then we can draw this rectangle. So C2, C3, and C4. And the point of drawing this rectangle is that we're going to now show that the integral along C2, C3, and C4 are all small in some sense. And of course, the integral along the entire thing by Cauchy's residue theorem of x to the s ds over s is 0, right? Because there are no poles in this region. And of course, the integrand is holomorphic. So how do we bound the integral along C2, C3, and C4? Let me give coordinates to this point. So let's say this is m minus it, and this is m plus it. So the integral along C4 is going to be m minus it to m plus it of x to the s ds over s. And then here we can use the triangle inequality, right? We can just take the absolute value of the integrand. And because x is assumed to be between 0 and 1, m is a large real number here, this is going to be less than x to the m, over t or over m or whatever, so it's decaying exponentially in m. So we can take m to be as large as we like, and this is going to be smaller than, this is going to be however small we want. So there's no problem here. I mean, at the cost of making C2 and C3 longer, but we'll see now that we can make C2 and C3 as long as we want. Okay, so what about the integral along, say, C2? C3 will be similar, so this is sigma plus it to m plus it. And then again, we can use the triangle inequality, and we can say that this is less than the integral sigma plus it to m plus it of just x to the sigma ds over sigma. So that's going to be x to the sigma, and then we can do ds over t if we like, because sigma was assumed to be positive, so this is the modulus of s is greater than t. Okay, and then this is going to be well, this is going to be x to the sigma over t, and then we're going to have a log x in the denominator. Okay. And then, of course, the bottom part of the rectangle is exactly the same. Okay, so what we get for all of this is that the integral sigma minus it to sigma plus it in the case where x is a positive real number between 0 and 1 of x to the s ds over s is equal to 0, because that's the sum of the residues, plus big O of x to the sigma over t log x. And now sometimes it'll be nice to have, if log x is close to 0 here, then actually maybe this is quite big. So here's an alternative way of doing it. What you can do is you can, so here's your s equals 0, and then you've got your vertical line, and you can take a circle. Let me try and draw a nice circle here. All right, good enough. So this is a circle with radius absolute value of sigma plus it, and if we look at, say, this contour right here and then coming back down, we see that the integral sigma minus it to sigma plus it, again, the sum of the residues is 0. This piece is the piece that we care about, and then this piece, well, we can just bound it by the circumference of the circle, and then the absolute value of the integrand is going to be at most x to the sigma, because again we're assuming that x is less than 1, and then the modulus of s is going to be the modulus of sigma plus it. So this is going to be, in fact, less than or equal to 2 pi is quite lazy. I mean, it's just the circumference of the circle times, well, okay, yeah, so this term altogether is the circumference of the circle times x to the sigma over sigma plus it coming from the modulus of s, and so of course these cancel, and so what that means is that we actually have the bound the integral from sigma minus it to sigma plus it of x to the s ds over s is big O of x to the sigma, and then we have a min 1 over t to t times log x. So the 1 is coming from doing it using a circle, and the t over log x comes from using a rectangle. Okay, so case 2 is x is greater than 1, and then what we find is, well, so here we're going to take a contour that includes the residue, because if x is greater than 1, then intuitively what's going on is that we have to shift to the left to get exponential decay. When x was less than 1, we could shift to the right and get exponential decay, but here, that it's going to blow up. So using exactly the same reasoning, but now we just have a residue in our contour, we get that the integral sigma minus it to sigma plus it of x to the s ds over s for x greater than 1 is 2 pi I, right? 2 pi I times the sum of the residues, and then we still have the same error term, O of x to the sigma min 1 over t absolute value log x. Okay, and case 3 is going to be x is equal to 1. In this case, you just don't have an x to the s here. You're just integrating ds over s that has an elementary antiderivative, it's log. And so what you get is that this is equal to pi I plus probably the same error term, if you work it out. And usually in practice, you don't really want to take x to be an integer. Anyway, so this is not really going to come up. Okay, so we have this building block, and now why do we care? Well, we care because if we have some Dirichlet series, some n equals 1 to infinity of an over n to the s, and I'm going to assume that an is n to the omega for some real number omega. Okay. Then we want to take the inverse, we're going to want to take the inverse Mellin transform of Dirichlet series a lot. That's going to be the integral, say 1 over 2 pi I sigma minus it to sigma plus it sum n equals 1 to infinity an over n to the s x to the s ds over s. And here we're going to assume that sigma, let's just take it to be 1 plus omega plus epsilon for some small epsilon that may change from line to line. And the point of doing this is that now this Dirichlet series converges absolutely. And that means that we can change the order of integration. So what we get is sum n equals 1 to infinity of an, and then we have our integral, which we had just worked out above, essentially. Here it's, instead of x, we have x over n to the s ds over s. And what we found above was that I'm going to assume that x is not an integer, so we don't have to worry about case 3 of x being 1. So what we found above was that essentially this quantity, this integral, is 0 if x over n is less than 1, and it's 2 pi I if x over n is greater than 1. So what we get is that this is going to pick off the sum n less than x of a sub n, of the Dirichlet coefficient. So this is a very, very useful fact. This is a very convenient way to get a partial sum of Dirichlet coefficients, and we're going to use it a ton. But then we have this error term, right? So the error term is going to be omega of sum n equals 1 to infinity of, say, absolute value of an, x over n to the sigma, and then we have min 1 over t absolute value log n over x. And here, it's x over n, but because of the absolute value, we can flip the log over, and it's a little bit more convenient to write it this way. Okay, so we have this error term, and we want to be we want to make this error term a little bit more convenient. So let's start working on it. So the idea is going to be to split this sum up into two regions essentially. So let's start with the region n. So it's the sum n from 1 to infinity, and we're just going to say that n is at most half or at least double x. So n is not going to be in the interval x over 2 to 2x of this quantity. And then here we're going to have x over n to the sigma. And in this case, this is, we're going to have we're thinking of t as being large here. So this quantity down here, this is at least log 2, and t, just take it to be take it to be at least 1 over log 2. So we don't have to worry about the min 1 here. It's just going to be 1 over t log n over x. And this is, like I said, this is at least log 2, so let's just bound it that way. And what we end up getting so we can write it this way. Here now I'm just going to sum over all n, but I'm going to say that this term is at least a constant, log 2, and then I'm going to omit it. So we get an x to the sigma over t, and then here we have an a sub n over n to the sigma. This part doesn't depend on n. This is essentially a value of the Dirichlet series, and remember we've assumed that sigma is at least 1 plus omega. So this sum here converges absolutely. So this is just okay. Cool. So this part was easy to deal with. The other part is a little bit trickier to deal with. So now we're going to look at the sum x over 2 and 2x of absolute value a of n x over n to the sigma, and then here we have a 1 over. Now we have to care about the min. Okay. And the idea here is that when n and x are comparable, what we have is that log n over x is going to be, I'm going to write this symbol to mean within a constant factor of, it's going to be within a constant factor of x over x minus n. Okay. And this just comes from, say, looking at the Taylor series. So what we can do here is we can omit the value of n, which is nearest to x. So let's just say n minus x should be strictly greater than 1. So don't take the nearest integer. And well, so now what we can do is we can say that this sum, so this part here is bounded by, say, 2 to the sigma, and sigma we're thinking of as being fixed here. So I'm just going to drop that. I'm going to put that, in this less than the implicit constant. And then you have the sum x over 2 n to 2x, and then n minus x is greater than 1 of the absolute value of an. And then for this piece, what you can do is, let's replace it with this. So we can write, say, x over t times x n. And for this part, let's take our an and we'll use the assumption that an is less than n to the omega for some omega, and n is about x, so this is going to be something like x to the omega. Right? So what we do when we substitute that is we get the sum over the same thing of x to the 1 plus omega over t, and then x minus n. And here, when we're thinking of summing over n, and this quantity is at least 1, we can essentially approximate it by an integral, and we're going to get some log, right? So this is going to be less than x to the 1 plus omega plus epsilon over t. Again, just essentially thinking of integrating in n here, so we get basically a log x, and that, I'm just going to write that as x to the epsilon. And then we still have to deal with the handful of terms, where n is within an integer of x, and then there we can use the min 1 part, and we get sort of just an x to the omega, right? This part is negligible. And then remembering how we defined sigma, we took sigma to be 1 plus omega plus epsilon. I mean, possibly for some different epsilon, but that's okay. We can just write that this is less than x to the sigma. Well, you end up with a plus epsilon here because to be safe, basically, right? Because you may not have exactly the same epsilon or something. I don't really remember, honestly, but you end up with an epsilon here. So ultimately, what you end up getting is that the integral sigma minus it to sigma plus it of sum n equals 1 to infinity of some Dirichlet series an over n to the s, x to the s, ds over s for sigma is at least is such that this Dirichlet series converges absolutely. What you end up getting is with a 1 over 2 pi I, and x not an integer, is the sum n less than x of the Dirichlet coefficients, and then the error term you end up getting is x to the sigma plus epsilon over t. And this formula is what I'm going to call Perron's formula. And it is super, super useful. We are going to use this all the time to evaluate our partial sums, right? Because this sort of thing, these partial sums of Dirichlet coefficients, this is going to be the primary thing that we end up being interested in. So having this way of getting at them and having this error term that's explicit, I mean, this is going to be the main tool that we use throughout the